So now we will discuss in details about the depth and the lateral resolution which we can obtain while doing micro PIV. So since it is very different from macro PIV and there are other complications related to micro PIV systems when it comes to the resolution, we'll discuss all those details in the upcoming slides. So what do I mean by depth resolution? So by depth resolution, what I want to say is that how well can you resolve or visualize the flow field having cedar particles obviously in the direction of the axis of the objective lens, that is the depth of your channel. Now if I show you a schematic here, you can see, suppose you have a micro channel like this with these coordinate system, the x direction and the y direction and the z direction. Z is the depth basically, and if you visualize the micro channel from bottom, so you see that you want how much you can actually see the particles in this z direction, like what is the region till where, or what is the plane in which you can actually focus all the particles very well. That would give you the resolution in z direction or the depth resolution. And the other thing is the lateral resolution. What I mean by lateral resolution is that how well can you resolve or visualize the flow field having zero particles in the plane of interest. Now for example, you have this. Now if this is the plane of interest, then how well can you resolve the data, the particles, using your optical system in this plane? So basically, like, so you can see two vectors popping up here, and how much distance you can get between those two vectors, or how well you can resolve the vectors. And this is very important because this is the thing which you want to get accurate output from your data when you image the basically flow field using the camera and the cedar particle system. So the output actually, as I showed you before also, that how well you can get the spacing between the vectors which to get meaningful results. So again, it is very important to understand the capacity and limitations we face while performing micro PIV experiments in terms of resolution. So before starting any of the experiments, it is very crucial that one perform some mathematical calculations to understand his or her system. Basically, what kind of lens you have, what is the objective, what is the microscopic objective you are using, what is the magnification, and then the numerical aperture, and what is the depth of your micro channel, the material of your micro channel. All these things play a significant role in resolving your flow field. So we'll be discussing about those things here. So basically, again, as I told before, how well can you resolve the distance between two vectors? That is what is the question. Now suppose this is one of the interrogation window and you can see some particles inside it. Now the particle size in case of micro PIV can be really small, as we discussed previously, that it can be in nanometers, and it can even be lesser than the wavelength of the light you are using to visualize them. So suppose if we use the green light to visualize that, don't go by the color of these particles because it won't look like this. This is just for visual representation. So suppose if the particle is around 300 nanometers in diameter, and which is lesser than the wavelength of the green light, that is around 532 nanometers. Now normal scattering won't work here. So in such cases, when the particle size becomes smaller than the wavelength of the light, inelastic type of scattering occurs, where that's where we use fluorescent detection techniques, and there are other techniques, but we won't go into depth of others. And about inelastic scattering, I mean, you can read about it, and basically the internal state of the particle alters after they collide, and their normal scattering doesn't work. So this is one of the complications which we deal by using fluorescence detection techniques. So in comparison with the macro PIV system, where the glass spheres, normally we use the glass spheres, or the tracer particle used are mostly of the order of 10 microns or greater than that, maybe 40 to 50 micron also, which is much larger than the wavelength of the light. And in that case, basically light means, from light, when I say light, we normally by default assume it to be the green light, which has the wavelength of 532 nanometer. And in this case we see Mie scattering, which actually is proportional to the square of the particle diameter. So if you increase the size of the diameter, size of the particle, tracer particles, in case of macro PIV, so a lot more scattering will take place, so more light will be falling on your camera sensor. However, there is again this catch where you cannot increase the particle diameter to certain limit, because again the Stokes number would become very large, and the particles won't follow the path faithfully. So again there is a trade-off, and which I think Professor Basu has discussed in depth in his PIV lectures. But yeah, I have brought it up here just to highlight the difference in the macro and micro PIV systems. So basically, if you have a test section like this, and now you this is a large scale test section, you can assume it to be in the orders of centimeters. So suppose this is like 10 centimeter by 10 centimeter, and then if you want to see a plane, you use a laser sheet, basically green light laser sheet, to illuminate a single plane, and you can see these particles very well in this plane, and basically the light gets scattered perpendicularly to the direction of the camera, and it falls on the camera sensor, and you can actually record the image exactly in this plane. And this thickness of this light sheet can vary from 1 to 2 mm. Now this is all good for macro systems, but what about micro systems? Like in case of micro system, we don't even have the thickness of the channel as big as 1 to 2 mm, that is almost around 2000 microns. So what we deal with is like with 100 microns or 50 microns or maybe 10 microns also many times. So how do you solve this problem? If you use this laser light for your micro channels, basically of the order of 10 to 100 microns, the light would flood the whole channel and you will be seeing everything inside it, right? So what you will get, so what you will see is basically a region, a huge region which is not desirable most of the time. So instead of using a sheet, basically if you actually are able to modify the laser sheet to a thickness of say 10 micron or say 50 micron, even then aligning that small sheet of laser light along with your micro channel can be very difficult, because you are dealing in precisions of micron level. So what is done instead is a volume illumination technique is used. Here a volume of the micro channel is illuminated, and depending on the need of the experiment, like whatever depth you require, you can actually adjust using some kind of optical modification. So what I am trying to say is, suppose you have a micro channel here, and suppose the flow is of plane Poisley flow inside that, and you are looking, you have a basically laser system which is behind this, basically that's the bottom, and you are looking from top. So you can say that at any section, say suppose at this section, suppose at this section somewhere, you have the profile like this. It's the classical parabolic profile where you have a larger velocity at the center, and due to the no slip the velocity goes on diminishing near the walls. Now if you see this whole region, what you will be seeing, what you will be capturing is particles of varying speed across the depth, right? I mean you will also capture particles moving much faster and also capture particles moving much slower. So what you will actually get is a depth averaged velocity field and not an in plane measurement, but many times we need velocity field in a single plane, so we need to concentrate on a smaller region. Now for this what we can do is we modify systems, like we modify our optical system which allows us to focus only on a narrow plane. So to illuminate a small region of the microchannel, we need to find out the depth of field of our microscopic objective. So we'll talk a bit about the depth of field, the concept of depth of field. So suppose you have a point object here, I'll just on my pointer, yeah. So suppose you have a say point object that is here at the object plane, and the light that passes, light coming, and this is basically the lens, okay, the lens, I hope it's clear, and this is the sensor plane of sensor of the camera, or the image plane where you want the image to be formed. So the light rays will go through this lens and it will form an image at this point, right? Now let us assume that this point, this object plane is exactly at that point where it is actually forming a very sharp and focused image of the particle. So this should be the arrangement for that. Now suppose your particle is shifted a bit away from your lens, right? So now if you draw the light rays, it should look like this, and what will happen is the rays will start to converge a bit earlier than the image plane, and you will get an image which is a blurred image on this sensor or the image plane, which should look something like this, and we call it out of focus. Another situation that can occur is that if your particle is brought closer to the lens here and not at this object plane, then if you draw the rays, it will look something like this, and the image and the rays will actually converge somewhere behind the sensor plane or the image plane, and you will get the image which is again a blurred image and out of focus. So now how we define the depth of field is that now the distance between this displacement of the particle from the object plane and this displacement ahead near to the lens is given as delta, and this is basically the depth of field of the objective. But how do we actually define it? I mean, how do we know that this delta is enough, because you can take this particle much behind and you can take this much nearer to the lens. So now this is a trade off again, and you have to decide that, okay, suppose till this distance, if your particle is somewhat in focus and which is acceptable basically, then you can use that as one of your limits. And even in this case, when you bring the particle near to the lens, and if you are getting an out of focus but it is somewhat acceptable, in the acceptable range, then you can consider this to be the other limit. So say for a range of length, say delta, the images are in the acceptable range of focus, and from here to here is basically the distance which is known as the depth of field. So basically the objective we assume that the objective will be able to focus over a depth of delta. So again, now we have found out, say suppose our delta is some x micron. So again, if our now the depth of our channel has to be greater than that x micron, because so that we are only able to see a small volume of the microchannel, or say small in focus plane of the microchannel, and not a very large section. So for that delta has to be smaller than the depth of the micro channel. So now we'll see again, like suppose a bit more about the depth of field. Suppose you have this micro channel of height h, and this is the, say, the coordinate system. So if you are viewing it from bottom, so what I want to say is that this is the depth of field I am talking about. I mean, you can see a bit of a gap here, and this is the region for which you are able to basically focus the particles. And in a two-dimensional figure, you can see it something to be like this, and this is basically the depth and delta. And now you can see that you are able to only view this much of the region and not a much larger region. So this will give you much better results over a smaller range of volume. And if we start to define the depth of field mathematically, then the depth of field is actually given as sorry, n into lambda by Na square. Sorry. What are these parameters? So n is the refractive index of the immersion medium. So normally immersion medium is used on top of this objective, this area where I am highlighting, and this actually helps to increase the numerical aperture. And if and this n is equal to 1 if there is nothing but air, and if this n can be actually around, say, 1.4 to 1.5 if you are using some oil immersion on top of this objective lens. So this is very important, and you can change these things as per your need during your experiments. And lambda is the wavelength of the light, and normally we use a green light, so it's around 532 nanometers. Then the numerical aperture Na is defined as n into sin theta, where this theta is the half angle of the objective collecting cone. So basically if you do something like this no, okay, I'm sorry, this up. Suppose something like this. So this angle basically, just pardon my drawing a bit, this is the theta, this is the half angle, and basically you will have your objective here somewhere here. Yeah, so this angle is defined as theta, and the numerical aperture is actually the product of the refractive index of the medium here, medium in between between here and the sine of this half angle. So from this relation you can see that if we have a higher numerical aperture, the depth of field is lower, and if the depth of field is lower, basically you can see much more smaller features inside your micro channel. And basically the numerical aperture is nothing but the light gathering power of the objective, and normally we prefer it to be larger, but again it has its own pros and cons. So now this is really important, that is why we are studying all this, because the focal depth of the microscope objective may not accurately represent the out of plane resolution particles, and that is because particles that are near the focal plane, I mean, say you are focusing somewhere here, if there are particles that are up slightly near to this focal plane, that can also influence the correlation peak. A slight, say, you can actually get some illuminations from those particles also, so which can actually increase some kind of noise or something like that in your correlation peak. So that you have to take care of while designing your algorithm, which we will talk a bit more in depth in the upcoming slides. So now let us find the depth of field for some of the microscopic objectives that are commonly used we'll find for a 4x and a 40x microscope objective with the numerical aperture values of 0.1 and 0.65 respectively. We'll consider a green light source having the wavelength of around 500 nanometers. The immersion medium is air, that means your small n, that is the refractive index, is 1. So, to find the depth of field for a 4x objective, we use this formula which was discussed previously, and if you put the values, that will be 1 into 500 by 0.1 to the power whole square, and you get a value of 50 micron. Now you can see that for a 4x for a 4x objective you get a depth of field of around 50 micron. So it looks like a very large depth of field, but that again depends if your gradients, or say if the flow you are trying to visualize is well between, like well within the depth of field. If your flow you want to visualize is say a larger, much larger, say around over 200 microns, then this 50 micron should be sufficient for you. However, in microfluidics normally we work with very smaller depth of fields, so normally 50 micron gives you a depth averaged velocity field and not an in plane velocity field. Again, everything is very subjective to what you actually want to see, and for a 40x objective, if you calculate, you will get around 1 microns depth of field, which is much smaller, and here you can actually focus and on a very smaller region, and you can see an in plane velocity field. So if you have basically a low NA lens, you get depth average velocity field, and if you have a higher NA lens, you can see you get depth in plane velocity. So basically it depends on what kind of a system you want to use for your experimental setup, and according to that you can change the numerical aperture, you can change the objective and even the green light source, but then normally we change the microscope objective and the numerical aperture by changing the say refractive index and those kind of things. Now I'll talk a bit about the implications of volume illumination. So by now you must have understood what we mean by volume illumination, and it can have severe implications because unlike macro scale phenomena where you can easily get the data in a single small plane of interest, in case of micro PIV you are using microscope objective which itself has its own depth of field depending on the optical system. So it is very subjective, and it can be a tedious task many a times to get the desired depth of field you want. So understanding volume illumination phenomena is really important, and I'll just give a brief talk on that. The slide will be a bit busy, but you have to read it out if you need to know a bit more about these things. So what I mean to say is an important consequence of volume illumination is that all particles within the illuminated fluid volume emit light, and including those outside the focal plane of the imaging optics. So that's what we discussed previously also, that because of this volume illumination, the particles that are actually a bit out of focal plane also, they also start to emit some kind of light, and these out of focus particle actually can contribute significantly to the background noise. And this term called signal to noise ratio, which is one of the most important parameters while assessing your post processing data. So if your signal to noise ratio is very high, then it's better, because that shows that the noise compared to your relevant signals are very low. However, if your background noises starts to pop up, starts to become significant, then this S and R ratio becomes very small, and this can actually give inaccurate results. So one has to be very careful while processing their data and understand this concept of SNR. And a commonly used approach to improve the SNR is to reduce the particle concentration, or say if possible you can reduce the intensity of the light also a bit, but that doesn't help much. And another thing is you can also reduce the depth of your test section, but then that is not possible all the time, because you are performing a certain kind of experiment which requires a certain kind of depth of your channel. So normally the best way is to reduce the particle concentration a bit, and then look if your SNR ratio comes in a acceptable range. Another concept which is really important, which I'll be briefly discussing here, is the depth over which particle images contribute significantly to the correlation function we are talking about. And this depth is known as the depth of correlation, which has been a topic of considerable research. You can read a lot of papers on this topic. Here we are talking about the particles which actually significantly contribute to finding the correlation peak, right? So basically this is the most important thing, because this is what gives you the output which you want. Now how do you define this thing? There are a lot of definitions you can find in the literature, but one of them is basically the depth of correlation has been defined as twice the distance that a particle can be positioned from the object plane, so that the intensity along the optical axis is an arbitrarily specified fraction of its focused intensity. So basically there is a focused particle that has some kind of intensity, maybe let's call it as the peak intensity. Now you define a fraction of that peak intensity, say 1/10 of that intensity, and till a distance where you get that much of the intensity, you assume that the particle should basically contribute to the correlation, and if it goes out of that threshold, you basically discard it. So let us say that the cutoff can be assumed to be in arbitrarily 1/10 of the in focus intensity. So say your intensity is say 100 for something 100. So 1/10 of the basically you can assume that below 1/10 of 100 things will be neglected. So the correlation function, actually if you go into the depth and understand the correlation function, how it works, it actually varies like the intensity squared, so a particle with 1/10 the intensity of the focused image can be expected to contribute less than 1% to the correlation function, right? Because there is a intensity squared basically relation, and since you are thresholding it to 1/10, it will contribute somewhere less than 1% of to the correlation function, and this much is something which we don't want. So we can actually safely neglect it, and this will definitely reduce the noise that was coming in the like the noise in the image, and it will contribute and enhance the signal to noise ratio. So this depth of correlation is a very important topic, and one should also understand about it, and you can find a lot of it in the existing literature, which I am not discussing here in depth in the interest of the time. So basically, experiments for micro PIV must be designed so that the focused particle images can be observed even in the presence of background light from unfocused particles and test section surfaces. So I hope you understand the meaning of this, because now as we have seen that there are particles which can be present in the background of the focused plane, and there can be some kind of reflections and other things from the test sections also, but your experimental setup should be that robust that the focused particle images can be observed even in the presence of these unwanted sources of light. So now we will talk about the lateral resolution, that is the in plane resolution. We have discussed a lot about the depth resolution, where we saw the volume illumination technique and how you can get a desirable resolution according to your experiment by changing the numerical aperture, the objective, the magnification, and other optical parameters. So here we'll start talking about the resolution in a single desirable plane. So if you have studied optics previously, you must be knowing that due to diffraction of light, every optical system is restricted in its own resolution. So by this I mean that suppose you have a point object in the object plane and you want to see it in the camera sensor or the image plane, you won't be seeing it exactly what it is like. So suppose you have some diameter, suppose I'll just on my pointer. So there is a diameter of this point, but actually you see something else, that is another, basically an enlarged image of this, which is like a spot size feature, and this is actually the point spread function. And for an optical system with a magnification greater than 1, you can define this diameter of this spot size function as approximately as 2.44 into m, that is the magnification of the system objective, and lambda is the wavelength of the light divided by 2 times the numerical aperture. So what I mean to say is, basically you have a point size image, but you won't be able to see that exactly, but you will be seeing something like this, which is much larger than that point size image. We will do some illustrations to see how much larger image we see in reality. And in reality, say we have a point size, this basically our particle size will be say dp, so it will be much larger than this a single point source. So from this formulation you can see that if you have a higher numerical aperture, you will get a small value of ds, this diameter, and that will definitely give you a better resolution in the single plane, because now suppose you have this, suppose we have this dp, and if we are seeing this dp in our optical system, we will see something larger than dp, but we want to minimize that ds for that dp, right, to get a better or more accurate data. So you can change the numerical aperture to reduce this ds. So now as we saw that we can change the numerical aperture to change the ds to get better optical resolution of the system. Now if we do a convolution with the geometric image of the particle with the point spread function ds, or the diffracted limited image, which is the spot size function, spot size image, we can get the effective diameter of the tracer particle in the image plane, and which is actually given by this formula. Say we call it as DEFF, effective is equal to nothing but the square root of magnification into dp, which is our cedar particle diameter. This is basically the geometric image, and which we have studied in our optics, plus the ds square, and we call it the effective image diameter. Now if you want to find the basically the effective particle image diameter by projecting it back into the flow, we must divide it by the magnification, and we get the value of dE. So let us solve a problem to get a bit more insight about what we want to find and what we are talking about. And regarding the convolution technique, we won't be going into the depth of that, and you can study it from some literature available online. So let us see, let's find this dE value for a particle diameter, say dp is equal to 400 nanometer using a 40x microscopic objective, and the numerical aperture is 0.65, which is a high numerical aperture, and let's consider the light to be a green light source. So let us find the ds value first, and which is nothing but 2.44 into m into lambda by 2 into na, and if we solve it, if we put the values like this, we should get something like 40 microns. So basically this is the point spread function which we talked about previously. Now let us see what is the value of the geometric image, which is given by m into the magnification factor into the particle diameter, and if you solve this, you get a value of 12 microns. and if we start finding the effective diameter using the formulas we talked about previously, we'll get the value of D effective as nothing but 41.76. It can be made more accurate, but just for the understanding I will written this value, and you can see that ds dominates here compared to the geometric image, and you can change this domination by changing the numerical aperture and other things as we discussed previously. So finally the value of DEE will be nothing but 41.76 by the magnification factor, that is around 1 micron. So what we mean is that for this kind of an optical system where you are considering the particle size to be 400 nanometer, okay, this should be 400 nanometers, yeah, so just a second, yeah, oh no, sorry, I think this should be, let's consider it 300 because I have calculated for 300. You can see I have written 300, yeah, so this is fine. So yeah, a 300 nanometer particle will look like a 1 micron particle. So you can see a particle of the order of nanometers starts looking like 1 micron. So you see this error, there is a difference of around 700 nanometer in the diameter of the particle. So this is basically the problem you face when you are seeing the resolution in a single plane, and this is caused mostly by the diffraction of light, and this is mostly unavoidable, but you can improve it and you can take these calculations into account while doing your post processing, and then that's how you actually can reduce the error in your output. And yeah, I mean, using convolution the uncertainty in displacement can also be obtained, and if you do that you can see how to basically reduce the uncertainty also. So finally I'll briefly recapture what we have discussed in this resolution part, because this is really important when you are talking about micro PIV, and this is the major part where you distinguish between the micro PIV and macro PIV system, because the Cedar particles and those things all are fine, but if you are not able to resolve things well, then you won't be getting accurate results, and the method of resolving differs here a lot compared to the micro PIV system. So the first, so basically we'll try to answer the question how this imaging differs in the two systems. So the first thing is basically we have already discussed these things. So the Cedar particles are many times smaller than the wavelength of the illuminating light. So as we have talked about this before also, in case of macro PIV systems, the Cedar particles are almost of the order of 10 microns or to 50 microns, and those are much larger than the wavelength of the illuminating light, normally a green light source. But then in case of micro PIV you start going down to nanometer level scales, where the diameter starts to become smaller than the wavelength of the light, and this is where this imaging system starts to make a difference, and you start using techniques like fluorescent imaging to view the particle. The other thing is the illuminating source illuminates a volume of the flow and is not a light sheet. So basically it's a very relative thing. Basically how you define a light sheet, it can again be considered a light sheet if you are seeing it in a very larger volume of test section, right? So basically in micro PIV system we illuminate a volume of the flow and not a single plane, and unlike in case of macro PIV system where we saw that the region of interest is of much larger depth, where we can simply use a laser light of 1 mm to 2 mm thickness to resolve the particles in that region of interest. And the other thing which is really important is, because of as a consequence of using a volume illumination, the particles are imaged against the background of similar particles. that are obviously out of focus but can significantly contribute to the noise and the correlation. So, as we discussed, about the depth of correlation, which was like say beyond the depth of correlation, the intensity of particles will be sufficiently low to contribute to the correlation, and consequently it won't hamper your output much. But your system should be designed in such a way that your images are taken with a background of similar particles, and they don't generate a lot of noise, and they should not actually contribute to the correlation that gives you the ultimate velocity vectors.